right? So now without snooping on the out-of-sample data, how do we perform this act of deciding what lambda we should use? That is called a cross-validation, the practice of figuring out what regularization to use, or in the variable selection problem, which are the variables we should use, is cross-validation. So there are also many different methods of cross-validation. I'm just going to describe one example of to illustrate the spirit. So this is all the data. Okay, so the first thing we get the data is we just carve out of the set of data and say we never want to look at this until we actually decided on the final model we're going to deliver. And then we're going to use that part of data, which is true out-of-sample data, to decide how good our model is, to quantify how good our model is. But in the in-sample data, we don't use everything to train the coefficients. We want to take a fraction of this. This is the training data. And this is cross-validation data. So we use that cross-validation data to figure out what lambda we should use. And the cross-validation data doesn't have to be just a fixed, static part of the in-sample data. It can also, we can potentially use multiple versions of this. So within the in-sample, we can say, okay, this is CV, this is train. We're going to train two different models, right? And we're going to say, okay, this is cross-validation, and we're going to use both this part and this part to train the model. So basically, we can get multiple models and apply each model to the cross-validation to figure out if I train all these models onto part of this in-sample data and apply it to the CV, how good this model is. Basically, repeating this multiple times. For example, 5 times. If the cross-validation data is 1/5 of the entire in-sample, then I can repeat the procedure 5 times, right? Each time the cross-validation data is a distinct set from all the other cross-validation studies. That gives me more confidence that what I get is not just luck, right? So if I know a particular lambda is the best, I have more confidence this is actually the best instead of being just lucky, right? So this amount of cross-validation is, for example, this is called a 5-fold cross-validation. If each CV is, if each cross-validation data set is 1/5 of the in-sample data set. So basically, in the cross-validation procedure, you have a lambda and you have a JCV. So that's JCV is equal to your model trained on the training data, which is all the in-sample data except for the cross-validation data. You train the model on the training data and apply it to that cross-validation. Right, so that you get one curve that probably looks like this. And then you do this 5 times, you get 5 curves that may look all like this. Okay, and you average these curves to figure out this is my lambda optimal. And once you figure out that lambda optimal, you use that lambda optimal and train the data, train a model out of the entire in-sample data set and apply this to out-of-sample to finally assess how good your model is. That's the current best practice for regularization and cross-validation. All right, any questions on this? Yes?
What if in your initial, in the initial loss function, what if instead of having like a vector of AJs, you use a matrix and penalize the second dimension of the matrix? Like,
what if in my initial formula?
What if A is a matrix and then you penalize the second dimension of the matrix, and in the sum you sum over all of the components coming out of that? so that you're not, as you're reducing your number of parameters, you're not throwing away data, you're just combining them into different variables.
If if A is a matrix, what are these two dimensions?
One is m, and the other is some other arbitrary number, and that number is what you penalize.
So if I have a matrix, I have A, J, K, for example.
Yeah, so like AJK, Xij, but
Yeah.
then in the loss function right there, you sum over the resulting vector, but then your penalty function is lambda times what k can go up to.
So wait. So you have a K here, and do you sum over K or something?
Yeah. So
Like
So
K.
I guess no. There's like another sum inside. So you could say like
Okay.
A could be okay. I guess like A could be AK, which is a vector of just ones. Then there's a matrix between A and X that's K by J, and the maximum value of K is what you penalize with lambda. So that you're not like throwing away vectors.
So can you come up and write like what's your imagine the formula is?
Yeah. Do you want me to just write it on the board?
Oh, come and write it on the screen so everybody can see it.
Like,
Okay, so here is the same. So your model is slightly different. K equal to 1 to
call it L.
okay. What is J? So do you need to sum over J or something?
No, J is. I guess it's confusing. This is also in a sum, but so like C and X is a matrix product.
So then you need to then you need to sum over J also.
Like, so xi for within this sum I is fixed. So x is like a vector of length m, what j goes up to.
Yeah.
And then CJK is a matrix that's m times L, or m by L.
Yeah.
So that this is a matrix product that you end up with a vector of length L.
Okay.
And then you multiply it by A, which is also a vector of length L, but is defined so that A is always 1. It's just like a vector of ones. So you're sort of summing across. So like for X, you've got a vector, this is Xi. And then you multiply it by some other vector that's that's m by L. So I guess the way I've written it is that this is like a tensor product over J.
Mm-hmm.
And then your penalty is lambda times L. So what you're doing is penalizing making this matrix taller or shorter.
Yeah. Okay.
My question was just like, could you do this and would it be better then because you're not, as you're reducing your number of degrees of freedom, you're not throwing away data.
So,
You're just allowing it to interact in a different way.
my question about if doing this is you have a vector of ones times this matrix, right? So what you're imagining is you first multiply the matrix with xj and then multiply with the vector of ones. Right?
Yeah.
Equivalently, because you have the association rule, you can multiply the vector of ones with that matrix and then multiply with the vector. So then if you do that, would it be any different from just to do this? Except for the A would just be the vector of ones times your matrix.